Hello everyone. So myself Jay Krishna, Assistant Professor working in Department of Civil Engineering, Laxman Reddy Institute of Technology and Management. Previously I gave a lecture on about the finite element analysis, introduction, and what is the usages and disadvantages. So related to civil engineering. So coming to today lecture about the general steps involved in the finite element analysis. So what are the steps involved in the finite element analysis to find the results? It's several engineering problems we can solve by using these general steps. So coming to find the general steps, so this method we can use for two methods. So first one is force method and second one is displacement method. So coming to this is force method is also known as a flexibility method. Flexibility method. So displacement method is also known as a stiffness method. So coming to force method and displacement method, force method is the internal forces are the unknown of the problem. So to find the displacement here. Second one is displacement or stiffness method. Displacements and nodes are the unknown values. So we can find the forces here. So by using these two methods, so which method is more useful for finding the engineering problems is, so displacement method is more commonly used because it is easier to apply and find the most structural engineering problem. So entire FEM analysis we can use for the software. For displacement method we can solve the engineering problems. So finally it was two methods we can use for the displacement method is more commonly used for structural engineering problems. So we have a around 10 steps involved in the finite element methods to find the displacements and forces. So first one is step number 1, discretization process. So this is a flow chart, and second one is numbering of nodes and elements. Third one is selection of displacement function, and next one is behavioral of problem, and next one is stiffness matrix equation, and this one is assemble of element equations and applying boundary conditions and displacements and element stress and strain, and finally is results. These are total 10 steps involved in the FEM analysis. So go by one. So first one is discretization of the structure. So what is meant by discretization? Step number 1. So discretization means the structure can be divided into smaller parts is called discretization. So each part having an element. For example, I am taking it's a rectangular section. This can be divided into more number of parts. So this is the element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So element 1 is this one. So element 1, 1. So element 2, 2. So this is the rectangular is a one section, one element. This can be divided into several parts. This also one around 16 parts can be divided. So this is called discretization process of the structure. So why we discretization can be in this process? So it means so the entire structure can be calculated. It is very complex nature. So we can use for one by one. It is divided into smaller parts. Then it can easy to find out and solve the accurate value. We get the accurate value. So what is the final will? Accurate value we can find, so that we can divide entire structure can be some number of elements. So that easy we can accurate get the easy way. So this is the way of discretization process. So next one is elements. So based on the dimensions, elements can be classified into 4 types. So first one is one-dimensional element and two-dimensional element, three-dimensional and axisymmetric element. So based on the dimensions, we have 3 only. So this is the another one is for axisymmetric element. So coming to one-dimensional element. So one-dimensional element is example for bar element. It's a steel rod. For example, it is a steel rod. So we have there is only for line. It is a bar or line. Element. It means we have only 2 nodes. The only for length is having a only length, no breadth and depth. So it's having only for length only, linear only. That is known as one dimensional element. We have only two nodes. First one is one node and second one. There is no three node, third node. So this is the best example for the one dimensional element. So next, coming to second two dimensional element. So this is the bar element. So this is the line. So we have a two nodes, one and two, starting and ending. This is the start point, this is the end point. So next one is usage. So what is the usage for one dimensional element? So we have a stress problems like a thin plate and mesh plates are made using for the one dimensional elements, and plane strain problems like dams and tunnels, and plate shell structures like a shell structure, roofs and trusses, and aircrafts and tanks. These are the usages for three waves, trusses and strains and shell structure we can use for the one dimensional elements only. So next one is two dimensional element. We have, because one dimensional having only length direction only, but coming to two dimensional we have two dimensions. It means length and breadth, length and breadth only, length and breadth. So L comma B, we have a this element having L and B. So this is the example for triangular and rectangular. Rectangular having B and D, B and D, we have two dimensions. So that's known as a two dimensional elements. So example for a rectangular and triangular element. These are the two examples for the two dimensional element. Two dimensional having two dimensions. It means two ways, x and y direction. It means x and y directions. Next, coming to usage of two dimensional elements like mission blocks, engine parts, foundations, columns, concrete beams. Concrete beams also having B and D. B and D. So this is the concrete structure, beam. So involved in the stresses and strain and temperature variation for all directions. So these are the usages for two dimensional problems. Next, three dimensional element. So three dimensional element having simple example x comma y and z direction also including here. So in first one dimensional element only x direction, two dimensional element comma x and y direction, and three dimensional elements having x and y direction. It means tetrahedral element and hexahedral element is the example for it's a cube. It is solid structure. It is a solid structure. It's treated as a three dimensional element. Three dimensional elements having three direction, x and y and z directions. X and y and z directions. This is the three dimensional element. So next, coming to second, step number 2 is numbering process. Step number 2 is numbering process. So what is the numbering process? So what is the use of numbering process? In the finite element method, numbering process is the method of assigning the numbers, nodes and elements in structure to the computer can easily assemble and solving the global equations. So for example, I am taking the structure, this is a rectangular element. So we have a divided into number of elements. So this is the 1, 2, 3 and 4 and 5 and 6. So this is the element 1 can be divided again 6 parts, 6 elements. So we can use for numbering system. So it can easy to compute the easy to solve the global equations. Otherwise it is taking for difficult. So whether it is a element 1 or an element 2 or element 3 or 4 or 5 or 6. So we can use for numbering system so that the computer or manually we can analyze for easy to solve the problem. So in this way we have two types of numbering systems, longer side numbering process and shorter side numbering process. So coming to first one is longer side numbering process. So this is the longer side numbering process. This is the, for example, I am taking, it is a rectangular section. So we have divided into 4 parts. So this is the 1, 2, 3, 4, 5, 6. So can be divided into 6 elements. So I am giving the longer side numbering system 1, 2, 3, 4. Again 5, 6, 7, 8, 9, 10, 11 and 12. We have 12 nodes. So each node, each corner having a one node. So this is the 1, this is the 2. This is 3 and 4. Totally we get 12 nodes. 12 nodes. So this entire rectangle element is 12 nodes. Okay, now this is the numbering process of longer side. So how to find out the minimum number of difference of numbering nodes means maximum number of element minus minimum number of elements is equal to the minimum nodes. So it means, for example, I'm taking element 1. So element 1 having 1, this is 1, 1, 2, 5 and 6. 5 and 6 is the, and 1 and 2 is the numbering. So this is the element having maximum number nodes means 5, 6, sorry, 6. 6 minus 1, we get 5. So 5 is the difference of maximum node. So this is the example. We have 24. We have 24 nodes. So coming to first element 1. So which one? So element 1 I'm taking here. Element 3. You're taking for element 3 this one. So which is the maximum number node is 10. So minimum is 3. So 10 minus 3 we get 7. This is the numbering system to calculate the element for each element. So why we using for numbering system is it is easy to solve the problem. Okay. So next one, shorter side. Shorter side means we have, so this is the shorter side. So 1, 2, 3, again 4, 5, 6, 7, 8 and 9. This is the shorter way we can mention the numbering system of nodes. So this is the example. Here also same. So taking element 3 is example. So this is the element 3. So maximum is numbering is 14. 14 minus minimum is 9. 14 minus 9 is 5 is the difference of node numbering system. So this is the most important for numbering, for calculating, easy to solve the problem. So next, numbering process. So which one is mostly we can use for the solving problem? So it means shorter numbering method is more we can use for finite element method analysis. Because why? Because reduce the memory requirement and make the analysis is more efficient. So we can reduce the memory using for short numbering system. So and easy to efficient to solve the problem. So we can use for the shorter numbering process in the engineering problem. Next method is step 3, selection of displacement function for interpolation function. So coming to interpolation function, so displacement function if each element the polynomial function. So coming to polynomial function, we have a two polynomial functions, linear and quadratic. So because once we get the numbering systems to apply the polynomial function, whether it is a linear or quadratic polynomial function, we get the accurate value. So because every element having some boundary conditions, by using polynomial we get the accurate value of each element. To combine all the elements we get the accurate value. So individually we can solve, and combine all the elements we get the exact value. That is the main advantage of these steps involved in the FEM. So coming to displacement function, interpolation function, we find the easiest value. So coming to first one, interpolation function. So we have a linear and quadratic functions. Okay. So coming to linear one. So linear one having a first degree polynomial function. Okay, linear, one dimensional. One dimensional means it is a first degree polynomial function using for phi of x is the field value. So a0 plus a1x. This is the one dimensional, and two dimensional means a0 plus a1x plus a2y is the x and y direction. So up to a2y. So it's three dimensional up to a3z. So because the main point of this polynomial linear function is this is a straight way to variation. There is no curvature for giving the straight line variation of the field inside the element. There is no curvature to follow the accurate exact value. This is only give for simple and give the straight line variation of field values only. Next, coming to quadratic polynomial function, we have a second degree polynomial. It means a2x square. So a0 plus a1x plus a2x square. So this is the one dimensional quadratic polynomial function. So here similarly two dimensional and three dimensional, a2y and a3x square plus axy plus a5y square. So we have a x and y direction for two dimensional carefully. Okay. So coming to three-dimensional x and y and z direction. So up to z we can the inside the element. Okay. So coming to this main quadratic lateral function is quadratic interpolation function capture the curvature and typically gives more accurate value compared to linear geometry. So compared to linear geometry, the quadratic interpolation function is give the more accurate value because it is capture the curvature also. So that is the main advantage of quadratic polynomial function. Next, coming to material behavior for using stress and strain displacement function or stress strain relationship. So this is the step number 4 for steps. So first one is stress and displacement relation, strain and displacement, and stress strain relationship. So first one is strain displacement relation. So we have a strain E represent E du by dx. It means displacement with respect to x direction, displacement at u. So displacement at u with respect to x direction is moving. This is the strain displacement relation. Strain is directly proportional to displacement with respect to x direction. With respect to x direction, that is the relation of strain and displacement relation here. Next, stress strain relationship. We know that everyone Hooke's law says that stress is directly proportional to strain. Stress is directly proportional to strain. This is Hooke's law says that. So similarly, stress is equal to Young's modulus into strain. This is the constant value. So stress is directly proportional to strain. We have stress is equal to Young's modulus into E. This is the Young's modulus constant. So next one is derivation of element stiffness matrix equation. This is step number 5. So we have a stiffness matrix represent the K is equal to stiffness and U is equal to displacement is equal to force vector. It means it is the combining of each element. So element యొక్క display stiffness and displacement and force, nodal forces. This is the way to write the stiffness matrix for each element here. So next one is assembling of element equation obtaining for the global total equation. So it means step number 6. So before 5 we have a individual you can calculate for each element equation. So coming to sixth one, step number 6, combine all the equations, we get that is a global equations. That is a global equation. So write F is equal to force is equal to stiffness into displacement. That is a global equation. Combine all the forces here and combine all the elements stiffness here and combine all the displacements elements here. So that is called a global equation to find the matrices. Next, applying after writing the global equations, global stiffness equation, apply boundary conditions. Apply boundary conditions as per fix 0 to -1 to +1 or 0 to 1. We can use for boundary conditions here. Okay. So boundary conditions here. So this is the equation for global equations. So K is the stiffness matrix and boundary conditions fix the some points are here. So based on the support conditions. So next, finding the strain and stress from displacement, ninth one. So we have a strain and stress relation. So strain is equal to displacement with respect to x direction. So change in displacement at node 2 minus change in displacement at node 1. So x2 minus x1 means that is the ending point minus starting point. So we get the stress strain relation. Stress is equal to directly proportional to strain. We get the material property here. For stress and strain relation, we can use these two equations to calculate the relation of these two. So next, final one is results. There is a post processing. It means the name indicates post processing. It means after solving we need to analyze the understanding the result. that is called post processing. Once after everything apply boundary conditions, we get the analyze the one value, that is called result, that is called a post tensioning process. So computer programs help to view the graphical view and give the results for the graphical and color mode. Color mode give the software with graphical way. With the graphical way, we can show them the final view of the post tensioning process. So these are all 10 overall steps involved in the basic steps involved in the finite element analysis. Thank you.